3, 2, 1. Lift off. We are now doing space travel, part 2. First of all, though, we're going to read it, and you guys are going to watch the fire, because I'm going to light a fire, and then I'm going to read in the background. How about that for a story? All right, because this next bit looks like it's going to be juicy. If you can see, there's a gum container. What I've done is put a bit of fuel in it. So we're going to burn it. And as I'm reading the story, the 1966 version of what's going to happen in 1969, it almost sounds as if they've been to the moon already. Don't try this at home, folks, okay? I am a professional. There is fuel in that gum. Right, I'm going to carry on reading the speed of light. I'll be behind you, so don't panic if anything goes wrong. Oh, it's going faster than I thought. Ooh. The wood's only supported by nothing at all. By its own, by gravity, let's say. All right, so the space travel. Let's carry on reading what was said in 1966. Shall we? Bit of fun, isn't it, eh? So the fire goes. It should keep burning, I reckon. The countdown. Here we go. The countdown for a space flight begins about 48 hours before T0, liftoff time. Because of his long experience as a test pilot and his training in the spacecraft, the astronaut enters the last hours of the countdown calmly. First, he gets a final physical examination to make sure he is fully fit for the flight. After the checkup, medical specialists attach to his body a variety of sensors, devices that measure his pulse, breathing, blood pressure, and body temperature. How's that going? Yeah, so I can't see the action at the same time as read. Later, during the astronaut's flight, measurements from the sensors will be radioed back to Earth so that doctors can keep a running check on his condition. The astronaut then puts on his silver-colored spacesuit. During the flight, the suit will keep the pilot at a comfortable temperature. It will also supply pressure to protect him from the deadly vacuum of space if the cabin pressure leaks away. Don't go out on your fire. About 2 hours before T0, the astronaut rides in a lorry again. You'd think it would say truck. The astronaut rides in a lorry to the launching pad. He steps onto a lift. Elevator. Hang on a second, guys. Hang on a second. Where was this printed? Field Enterprises Educational Corporation, London. Chicago. Oh, I thought it was printed well. They're all from the US. Printed by Kingport Press, Tennessee, USA. Copyright 1966 by Field Enterprises Educational. God knows, but these are English words. This is how it's lorry, lift. It would be truck and elevator. Right, next we begin, where are we? Look there. Astronauts riding a lorry to the launching pad. He steps onto a lift that takes him up the gantry to the spacecraft, which is poised on top of the launch vehicle. Technicians help him to enter the craft and connect his spacesuit to the oxygen supply, the water cooling system, and various pieces of electrical equipment. The astronaut straps himself down on a specially designed couch. Next, he begins to check all his equipment. He makes a final report on the equipment and on his condition to engineers and medical men in the control center. We're burning, though, we're good. He continues to check his instruments as the vehicle's tanks are pumped full of propellants. Remember, this is 1966, 3 years before actual blastoff. Liftoff and launch. In the control center, tension mounts as T0 approaches. The astronaut steadily counts off the final seconds with the operator in the center. 5, 4, 3, 2, 1, ignition, liftoff. As the countdown ends, the engines roar to life, splashing flame and billowing clouds of smoke across the launching pad. The giant vehicle rises slowly at first, but gains speed steadily and then streaks into the sky. Is that going? Yeah. As the vehicle thunders away from Earth, the astronaut continues to report on his performance of the spacecraft and equipment. He feels the ship vibrate as it pushes up through the atmosphere. After about 2 minutes, the flight becomes less bumpy. Acceleration continues. As acceleration increases, oh, there you go. As acceleration increases, the astronaut feels as if his weight were increasing. Soon the pilot is pressed against his couch with a weight of well over 1,000 pounds. See, in English it would be settee. Strange. The launch vehicle arches over and heads for orbit. About 5 minutes after launching, the astronaut is soaring higher than 100 miles at more than 17,000 miles an hour. He is in orbit and weightless. Now, no force at all pushes him against his couch because he moves freely through space along the same path as the spacecraft. If he unstraps himself, he can push himself from the couch and float freely above it. In orbit, the astronaut sees a beautiful view of Earth and sky. Along the curving horizon, he sees a light blue band separating the Earth and the dark blue or black sky. If there are not many clouds, he can identify various land areas along his route. As he circles the Earth, the astronaut contacts tracking stations situated around the globe. He continues to report on the performance of the flight, first to one station and then the next as he comes into range of their radios. The stations in turn give the astronaut detailed information on the flight obtained from computers on the ground. Did you hear that? He continues to report on the performance of the flight, first to one station and then the next as he comes into range of their radios. I will say it over and over. Radio signals are probably exactly the same as light. They do not carry on if the radio is switched off. You're within range or you're forever out of range. If you're out of range, you won't be receiving a signal that left another radio an hour earlier and that radio is turned off. The signal, it doesn't sound right. The same as light. If the light source goes out, the light that the light source was radiating disappears as well. Alright, where were we? In the weightless condition, the astronaut eats by squeezing special food from a tube like a toothpaste tube. In this way, he does not make any crumbs that can float around and possibly harm some of the equipment. The space pilot may take a nap or sleep for several hours, depending on the length of his trip in orbit. During orbit, astronauts may take pictures of the Earth with hand cameras. They may also perform experiments with bottles of liquid to test the effects of weightlessness on the action of fluids. In one experiment, John Glenn was able to identify the city of Perth, Australia on the dark side of the Earth. Some astronauts have performed special exercises and tested certain head movements to see if any produce special space sickness, not special space sickness. In 1965, the Russian cosmonaut Alexei Leonov left his spacecraft 300 miles above the Earth. He wore a spacesuit and for 20 minutes worked outside the two-man craft. The orbiting astronaut can control the spacecraft and point it in any direction. He does this by operating a control stick similar to that of an aeroplane. Some astronauts can even change the orbit of their capsule because it carries its own rocket engine. Using this engine, pilots can steer the spacecraft into a rendezvous with a separately launched rocket. That is, they can guide the craft to lock its nose into place in a special opening in the other rocket. Re-entry calls for precise timing and aiming of the spacecraft when firing the retro rockets. The spacecraft may be aimed by automatic equipment, by signals from ground stations, or by the astronaut himself. In 1963, the American astronaut Gordon Cooper made a pinpoint landing by lining up his capsule and firing the retro rockets after his automatic system failed. What a luck. They just do this all of the time. They make stuff up. Which then makes everybody go, oh wow, that was close, not realizing that it's just BS. Oh God. Cooper made a pinpoint landing in this well-practiced but dramatic operation. The exact time to fire the rockets was determined by a computer on the ground. Cooper was then instructed to set this time on a special clock in the spacecraft. By radio, Cooper and his communicator on the ground counted off the last seconds, and the rockets were fired at exactly the right time. Of course they were. The astronaut feels the push of the retro rockets as they fire to slow the spacecraft. In a few minutes, he begins to feel heavy as the craft enters the atmosphere and is slowed down by the air. The searing heat ionizes the air around the craft and blocks out all radio transmissions to it or from it. For 4 or 5 anxious minutes, radar tracking is the only contact with the astronaut. Then voice contact is made again. The spacecraft releases its parachutes, which open with a slight jerk, and the spacecraft carries the astronaut gently to Earth. Dangers in space. The chief danger to men in space is that they depend entirely on the spacecraft that carries them. The machinery that gives them air, proper temperature, and control of the ship must operate perfectly under all conditions. In the future, pilots on long journeys may have to depend on closed ecological systems. These systems dispose of body wastes by using them to produce air, food, and water. They work by special chemical, electrical, and biological processes, including the growing of plants to produce oxygen and to serve as food. Meteors. These are the dangers, right? So meteors, even those the size of pebbles, could tear holes in the steel spacecraft. But collisions with meteors do not appear to be common. Scientists are trying to determine how many micrometeorites, particles of space dust in brackets, a spacecraft might run into, and to measure the effects of such collisions on the spacecraft. Radiation in space includes cosmic radiation, natural radiation such as Van Allen radiation, and an artificial radiation belt created by the high-altitude test explosion of a nuclear bomb. To protect astronauts against such radiation, spacecraft must have proper shielding to block the radiation particles. The amount of shielding depends on the intensity of the radiation and on the length of time the astronaut is exposed to it. But radiation is not dangerous in space flights that do not extend far. And the moon. Do we class the moon as extending far? All right. Let's just take another drink of water. This is all 3 years before going to the moon. Tracking a spacecraft. Manned spacecraft are tracked by radar. Tracking stations operate in various countries around the globe and on special ships in the Atlantic, Pacific, and Indian Oceans. These stations send their tracking information to a computer. The computer keeps track of the spacecraft's position and calculates where it would land if an emergency forced the astronaut to descend from orbit at any time. Most unmanned spacecraft carry a beacon that sends out radio signals. Tracking stations pick up the signals and use them to find the spacecraft's position. Some artificial satellites may be tracked by means of photographs taken with telescopic cameras. The pictures show the satellite's position against the background of stars. Groups of volunteers also help to track some satellites at night. Navigation and guidance. On long trips to the moon and the planets, astronauts will find their own position in space. Fly. Oh, go away. Where was I? Tracking stations on the ground will help the astronauts to perform the precise navigation necessary for their safety. Spacecraft cannot be launched on such a long journey with enough accuracy to reach its target. It must carry a rocket engine so that the astronauts can correct their course. Computers in the spacecraft and on the ground calculate the course correction from information obtained by astronavigation and by tracking. The course of an unmanned spacecraft can be corrected in a similar way. In this case, the spacecraft is controlled by special signals sent from a ground station. Space medicine is the study of how spaceflight affects man's body and his ability to work. Space medicine grew from aviation medicine, and it uses many of the same testing methods. The astronaut himself is the main source of information. Medical specialists study him carefully before, during, and after a spaceflight to learn the body's strengths and weaknesses in space. Doctors have learned that an astronaut can travel in space for several days without serious damage to his health. He can withstand the forces that act on his body during the launching and the return to Earth. He can eat, sleep, and work, repeat. Eat, sleep, repeat. Eat, sleep, dance, repeat. Eat, sleep, dance, repeat. And work on his body. His body is weightless during the flight. The space pilot's legs and ankles may swell slightly if he stays in one position for a long time without exercise. Doctors have also noticed that an astronaut's bones lose some calcium during a flight. But this is a common condition of people who lie motionless for a long time. So they went up there that long, 1960s and before, long enough to lose calcium. Doctors cannot tell what medical problems astronauts will face in flights that last weeks or months. Such long periods of weightlessness and confinement may prove harmful to the body. Astronauts will also meet new problems as they travel far enough to enter the radiation belts around Earth. Medical specialists must solve these problems gradually as astronauts make even longer and longer and longer flights. Right, here we go. Space travel, reaching the moon. It takes much more power to send a spacecraft to the moon than to place it in orbit round the Earth. To reach the moon, a spacecraft must be accelerated to about 24,500 miles an hour. As the craft races away from the Earth, gravity constantly pulls it and slows it down. When the spacecraft reaches about 200,000 miles, it is barely moving. But there, only 20,000 miles from the moon, the moon's gravity is stronger than that of the Earth. It begins to pull the craft towards the moon with increasing speed. The spacecraft may then strike the moon, or it may go into orbit around the moon. Aiming at the moon. The moon is a moving target. It travels around the Earth at more than 2,000 miles an hour. During the spacecraft's 60-hour journey, the moon moves more than 135,000 miles. For this reason, the spacecraft must be aimed at a spot in space 135,000 miles ahead of the moon, and it must reach this spot when the moon does. Did it not take them 102 or 103 hours to reach the moon? I'm sure it did. Here it says during the spacecraft's 60-hour journey. Orbiting the moon. Michael Collins. Orbiting the moon follows the same principles as orbiting the Earth. The spacecraft needs a certain speed to orbit at a certain altitude, but a craft that approaches the moon from the Earth may have more speed than it needs to go into orbit. It gets its speed by falling faster and faster under the pull of the moon's gravity. For this reason, moon-orbiting spacecraft carry extra rocket engines. The engines slow the craft and steer it into orbit around the moon. We just stop there. Apollo 10 got into the orbit position after leaving Earth, and it dropped to the moon and stopped within, 7 or 9 miles of the moon's surface. Took some photos and then shot back up. This right here, for those of you that believe this absurdity, well, unbelievable. Don't forget, all of this is 3 years before the moon landings. Landing on the moon. The earliest Lunix and Rangers sent to the moon simply crashed on the moon's surface and were destroyed. But certain instruments can be packaged in such a way that they withstand the shock of crashing. For example, the Surveyor spacecraft, which is designed to make a soft landing on the moon, carries an instrument called a seismometer to the moon. This device measures moonquakes and other vibrations of the lunar surface. Most instruments of all-manned spacecraft must land gently on the moon. Parachutes and wings cannot be used to lower the craft. These devices need air to work, but there is no air on the moon. For this reason, lunar landing craft must carry retro rockets that lower the craft to the moon's surface. I repeat, thrust in a vacuum sounds extremely fishy. Getting off the moon is much easier than getting off the Earth. The moon's gravity is only 1/6 that of Earth's. For example, a spacecraft that weighs 6,000 pounds on Earth weighs only 1,000 pounds on the moon. To return to Earth from the moon, a spacecraft must accelerate to about 5,400 miles an hour. This speed carries the craft to the point where Earth's gravity begins to pull the craft. Project Apollo. The United States government's plan for a manned trip to the moon and back calls for a special technique called lunar orbital rendezvous to get on and off the moon. The landing craft is called the Lunar Excursion Module. It descends to the moon from a lunar orbit after separating from two joined sections called the Command Module and the Service Module. These two sections remain in orbit until the return journey is started. To leave the moon, the Lunar Excursion Module blasts off into orbit to rendezvous with the Command and Service modules. Rockets in the Service Module then supply the power to send the astronauts back to Earth. Blast off. The first trip to the moon. See, they've got it all here. They had this stuff planned already. It didn't happen. It did not happen. It's ridiculous. It really is a ridiculous notion. 1969. Apollo 10 goes up in May and takes photos from 7 k's or 7 miles from the moon. It's just so stupid. Oh God, where am I? Blast off. On top of the giant Saturn V launch vehicle of Project Apollo, 3 astronauts wait for the final seconds of countdown in the Command Module. 1. At blast off, 7.5 million pounds of thrust lift the vehicle into the sky. 2. The first stage drops off. And 3. The second stage fires, sending the vehicle higher than 100 miles. 4. The second stage falls away and the third stage fires a short burst. 5. To put the vehicle into a temporary parking orbit. Travelling to the moon. When the third stage fires again, the spacecraft swings out of orbit and heads for the moon. 7. Adapters fall away, freeing the Command and Service modules, which are attached to each other to form a single unit. 8. The astronauts turn this unit round. And 9. Connect it to the Lunar Excursion Module. 10. The third stage is disconnected and course corrections are made. 11. The astronauts fire the Service Module's engines to slow the spacecraft. And 12. Place it into orbit round the moon. 13. 2 astronauts enter the Excursion Module. And 14. Separate it from the Command Module. The astronauts pick a suitable landing spot. 15. Descend from orbit. And 16. Land. 17. The third astronaut continues to orbit the moon in the Command Module. So that basically says, Neil and Buzz enter the Excursion Module, and 14, separate it from the Command Module. The astronauts pick a suitable landing spot, descend from the orbit. 17, Michael Collins continues to orbit the moon in the Command Module. Exploring the moon, the 2 astronauts take pictures and collect rock samples. After a day or two, 18, they enter the Excursion Module and blast off using the module's lower section as a launching pad. 19, they go into orbit. And 20, steer the module to connect with the Command Module. 21, they enter the Command Module. 22, turn the spacecraft round. And 23, disconnect the Excursion Module. Return trip bound to Earth. 24, The astronaut, I'm just reading the stages because they've got the stages all in picture form here. The astronauts fire the service module's rockets to blast out of orbit and head back to Earth. They check their course by sighting the Earth, the Moon, and the stars. And they also get information from tracking stations on Earth. 25. They correct the flight path to head for the atmosphere at the proper altitude and angle. 26. The service module is disconnected. 27. The astronauts return the command module round. And 28. Begin their re-entry. 29. During the descent, friction with the air slows the module and makes the heat shield glow. 30. The astronauts control the descending module and direct it towards the landing area. 31. Finally, the spacecraft releases large parachutes. And 32. The astronauts float to Earth. I mean, it sounds like a doddle, doesn't it? What's all the fuss about? Seriously, what's all the fuss about? Escaping Earth's gravity. The moon lies within the Earth's gravity, but at the moon's distance, the force of gravity is weak. Spacecraft accelerated to 25,000 miles an hour, just 500 miles an hour greater than that necessary to reach the moon, can escape Earth's gravity completely. And this speed of 25,000 miles an hour, about 7 miles per second, is called the escape velocity. It sends the spacecraft into interplanetary space. The craft then comes under the influence of the sun's gravity and goes into an orbit round the sun, close to Earth's orbit. The Earth itself circles the sun with a speed of 18.5 miles per second. A spacecraft launched from Earth travels as fast as this in relation to the sun. The craft's escape velocity is used up in getting away from Earth, and the spacecraft then orbits the sun at the same speed as the Earth. Escape velocity can send the spacecraft into orbit round the sun, but it cannot send the craft to a planet. Here we go, traveling to the planets. To reach a planet, oh, that fire's gone out, hasn't it? To reach a planet, the spacecraft must be accelerated from Earth to a velocity greater than escape velocity. This extra velocity changes the speed of the spacecraft around the sun. Given the proper velocity, the craft goes into a solar orbit that carries it to the target planet. To reach Mars, the spacecraft must be accelerated to 7.4 miles per second, 0.4 mile a second faster than the escape velocity. The craft must be launched in the same direction as that in which the Earth moves around the sun. The extra 0.4 mile per second then adds to the 18.5 miles per second the craft has because of the Earth's motion. The craft's final speed around the sun is 18.9 miles per second. At this speed, the spacecraft moves too fast to stay near the orbit of Earth. It coasts outwards from the sun until it crosses the orbit of Mars. And to reach Venus, the spacecraft must also be accelerated to 7.4 miles per second. But in this case, the craft is launched in a direction opposite to that in which the Earth moves around the sun. The extra 0.4 mile per second is then subtracted from the 18.5 miles per second, giving the craft a final speed of 18.1 miles per second. Well, we're in safe hands. At this speed, the spacecraft moves too slowly to stay near the orbit of Earth. It is pulled closer to the sun until it crosses the orbit of Venus. A spacecraft accelerated to the minimum velocity necessary to reach a planet travels along a path called a minimum energy flight trajectory. This is the course that requires the least amount of rocket power to reach a particular planet. In practice, planetary spacecraft are usually accelerated to a velocity greater than the minimum. With the increased speed, they reach the planet in less time. Reaching the stars. Present rocket engines do not have enough power to send a spacecraft to even the nearest star. Just to escape from the sun's gravity, a spacecraft must be accelerated from Earth to 14.5 miles per second. To travel to a star in a reasonable time, the spacecraft must go at a speed close to the speed of light. And that is impossible because the speed of light is absolute. There is no delay, is there? All right, well, I'm going to call that on this one. That's just about it. The history of space travel could be said to have begun 300 years ago. In the early 1600s, Johannes Kepler, a German scientist, developed the laws of planetary motion that describe the orbits of bodies in space. Today, these laws are used to determine the orbits of artificial satellites and to plan the flights of spacecraft. Here we go, see 1600s, and then in 1687, Sir Isaac Newton published his laws of motion, which used Kepler's work as a base. Newton's laws, as do Kepler's, form a cornerstone of space flight planning. For example, his third law states that for every action there is an equal and opposite reaction. This law describes why a rocket works. And that is your science. That is your explanation for thrust in a vacuum. It's ridiculous. Man, no wonder it has to get taught to children for them to believe it and then kick their friggin' have temper tantrums when they're told as adults that it didn't happen. For hundreds of years, many writers were fascinated with the idea of space travel. Many authors described imaginary journeys in fantastic spacecraft. NASA's done the same. As men learned more and more about the science of space, the stories became less fantastic. Some of the fiction of 10 years ago has today become fact. Right, that will do. Well, I started reading earlier on, and one thing leads to another. Can't help but mention again that in 1966 they still thought there was vegetation on Mars. 1966. But in 1676 they were looking at planets with a telescope. Oh, Roemer, he was working out Io coming out from behind Jupiter. I mean, 1676, that's 300 years earlier. And you're telling me that there was telescopes for 300 years. And in the 1600s, they made all of those discoveries, but we get to 1966, and they still thought there was snow at the poles on Mars, canals made by intelligent life, and vegetation. Talk about ridiculous. All right. It's told everybody exactly what's going to happen in 1969, the power of suggestion. And it happened more or less exactly as they said. So ridiculous, guys. Honestly, I can understand how children would believe this, but anybody else, it's a toughie, isn't it?